All right, so we are on problem 15. Hopefully everybody's doing well. Hopefully everybody.
I think you're muted.
Muted on Zoom, not muted on YouTube.
I think you're good now.
All good, okay. All right, too many things going on at the same time. All right, well, welcome everybody. Glad to have you here. So we're in problem 15. We've got 4 kilograms of water. So water, mass is 4 kilograms, temperature's 100 degrees Celsius, and it fills a closed container having a volume of 1 meter cubed. And then it says if the water at this state is a vapor, determine the pressure. If the water's two-phase, determine the quality. So I probably, instead of putting A and B, just I'll say find P, superheated, and find the quality if it's saturated. Okay. All right, so the first thing I need to do is figure out what phase it's in. So let me, excuse me. So define my phase, and in order to find the phase, in order to fix my state, I need to know 2 independent intensive properties. So 2 independent intensive properties, and I have a list of them. So temperature, pressure, specific volume, and if it's applicable, quality. So at this point I've got the temperature, and I don't have pressure, I don't have quality, I don't even know if it's relevant for this particular phase. The only other property that I might be able to get at is the specific volume, but of course I'm going to have to calculate it. It's going to be the volume divided by the mass. Should give us 0.25 meters cubed per kilogram. All right, so at a temperature of 100 degrees Celsius and a specific volume of 0.25 meters cubed per kilogram, what's our phase? So first place we go is our saturated tables, not because, I'm sorry. Okay. There we go. Not because we're saying it's saturated, but because we're using the information there to figure out what phase we're actually in. So table A2 has things organized by temperature. So at 100 degrees Celsius, if it's going to be saturated, then I know that my specific volume has to be between the V sub F and the V sub G value. So between 0.00105516 and 1.210 meters cubed per kilogram. And I can see that I'm in between there. Right? So I am between the V sub F, which was, remember it's already been multiplied by 1,000, 0.00105516 meters cubed per kilogram. It's between that and our V sub G, which was 1.210 meters cubed per kilogram. Okay, so it's saturated.
Sorry, I'm confused. Are we using the temperature for 110 or 100?
Guess it doesn't. It's going to tell us the same thing, but yeah, sorry about that. Thank you. So my eyes were crossed there. So this would actually be 0.0010435, and then this would be 0.673. Thank you very much. I appreciate it. All right, but still same thing. It is going to still be saturated, so great. So we do need to, well, I'll kind of make a note if I did need the pressure, it's just the saturation pressure, because we've determined that it's saturated, and there's only one possible pressure that it could be at, and that would be the saturation pressure. So 1.014 bar. We need to find out what our quality is. And so I'm going to use that kind of weighted average formula for specific volume as a function of quality and V sub F and V sub G. So I know, and I can pull this off at the top of my equation sheet, it's the V sub F plus my quality times the V sub G minus V sub F. So I'll just rearrange this to get quality. So it's V minus V sub F over V sub G minus V sub F, which is V sub FG. Right. So my specific volume, 0.25 meters cubed per kilogram, V sub F, 0.001035. Now it matters. Over V sub G, so 1.673 minus 0.001045. All right, and so I end up getting a quality, there we are, 0.149. And you could put that as a percentage as well. That's fine. That's what I got there.
Why are we finding quality again?
Because the problem said if it's two-phase, then you want to find the quality. If it were superheated, you were going to find the pressure. If you have any questions, please feel free to interrupt. That's fine. Stop me whenever. All right, so problem 16 has, instead of water, we're dealing with carbon dioxide, which is fine. We don't happen to have tables for saturated carbon dioxide, but they're going to provide the property data that we would need to look up in those tables regardless, so it doesn't matter. So let's go look at what it says. So we have a 1 meter tank. So I've put that here, 1 meter. Let's do this. There we go. So 1 meter tank, my volume meter, holds a two-phase liquid vapor mixture of carbon dioxide at negative 17 degrees Celsius. Okay. The quality of the mixture is 70%. It's that guy right there. For saturated carbon dioxide at negative 17 degrees Celsius, they do give us the V sub F and the V sub G values. So this is the stuff that you would be looking up in those tables anyway. Right, so I think that's kind of it. So what they're asking for us to give is they want the masses of the saturated liquid and saturated vapor in kilograms. So that's part A here. And then they also want the percents, the percent of the total volume occupied by the saturated liquid. So for part B, it's the percent saturated liquid, and I really should put by volume, right? So it's not by mass, it's by volume. Okay. So, I might not really know quite where to start. And sometimes that's the case, and that might be the case throughout the whole semester. You're not really sure where to start. So let's kind of brainstorm here. So we're going to list kind of the relevant equations or things that we think might be relevant. Brainstorms, that sounds exciting. All right. So we've got quality. We've got an equation for quality, which is, it's defined as M sub G over M. So it's the mass of the saturated vapor over the total mass of a two-phase mixture. This would be, of course, in a two-phase mixture, there's two things there, right there. Saturated liquid and saturated vapor. So we've also got an equation for specific volume. Close my office door. Public schools got canceled today, so my son, who's in 6th grade, is practicing his trumpet, and I can sort of hear it in the background. All right, so I've got an equation for specific volume as a function of quality. I've also got, this is also just volume divided by mass. And then there's another thing to note is that, yes, this guy, you know, this specific volume that I've written here, this is the specific volume of the two-phase mixture. But you could also define, I'm going to put it right here. I'll say by extension, you could say that V sub F, this is equal to the volume of that saturated liquid over the specific volume of the saturated liquid. And you could also say, same thing for the saturated vapor. It's the volume of that saturated vapor over the specific volume of that saturated vapor. So like I have some of these things, right? I got those V sub F. Oh, somebody's gonna call me on that. It's the mass. Mass. That's the mass of the saturated. Yeah, there we go. That looks better. Somebody was probably like, what? All right, so some of the things I do know. I know this guy right here. I know this guy right here. So that's the saturated, the specific volume of that saturated liquid portion and of the saturated vapor portion. I also know the total volume, and I know the quality. I know that guy, I know that guy, I know that guy. So actually at this point, I've got enough information to calculate that specific volume if I plug and chug, right? So let's see what that would be. I end up getting, this ends up being 0.01258. It's meters cubed per kilogram. Okay, perfect. I don't know. I might need that. We'll see. Okay. Well. So just kind of looking at what I've got. Let's try to get M sub G. All right. So I know M sub G is equal to, or wouldn't that just be quality times the mass? Right, and so I've got that information. Let's see if I can sort of, yeah. I look at this guy right here. I'm bringing him down. That's where I'm getting that guy. So I've got the quality, and I need to figure out the mass. And looks like maybe another place that I could look might be this guy. So that would get me mass, wouldn't it? So this would be my quality times my volume divided by my specific volume. Okay. So this would be 1 meter cubed over that total specific volume, which I just calculated, 0.01258 meters cubed per kilogram. So keep in mind, this is my mass. And my mass, if we wanted a number, I do have that, 79.46. So this right here is the total mass. And then if I look at kind of the other stuff I've got, oh yeah, I'm all ready, aren't I? So this times the quality would give me M sub G. So my M sub G ends up being 55.62. Right. I'm gonna box that. That's part of A. And then the other part is finding that M sub F. But remember, you know, we've got two phases. So you've got the mass is going to be the mass of the saturated liquid plus the mass of the saturated vapor. So the mass of that saturated liquid is just going to be mass minus M sub G, which is going to be 23.84. Perfect. Okay. So I've got that guy, and then the very last thing I need to do, so that's A, and then the last thing I need to do is find the percent saturated liquid by volume. So what I'm looking for is the volume of that saturated liquid over the total volume. Right? So I've got the total volume, it's the 1 meter cubed, and that big V sub F we'll get using that guy right there. So it's going to be M sub F times the specific volume for that saturated liquid. So this would be 23.84 kilograms. And then the specific volume V sub F, 0.9827 times 10 to the negative third meters cubed per kilogram divided by 1 meter cubed. So I end up getting 0.0234, and they wanted it in a percent, so 2.4%. Okay. Sad.
What does M sub F and M sub G stand for again?
So when you have a subscript F, it means it's whatever that property is associated with the saturated liquid portion of that saturated mixture. And then this G would just be for the saturated vapor portion. Because what you have, you know, they're talking about a tank. And now that I know, like, the percentage, like, as far as, you know, the volume, it's a really small percentage with the volume. So if I thought about it, it's like, I got this two-phase mixture, right? I've got this liquid on the bottom that's about to boil, but the rest of it has already boiled. It's already in the gas phase mixture. So that's physically what you're thinking of. It's a mixture of the two. But those two phases are existing in equilibrium with one another. So you've got water, you've got liquid water that's about to boil, and then vapor that's about to condense. All right, so problem 17. We've got water in a closed rigid tank. Initially is a saturated water vapor at 200 degrees Celsius, and it's cooled to 100 degrees. So initially at 200 degrees, it's a saturated vapor, which means that our quality is 1. And so that's kind of, when you write down your givens, you're always trying to be cognizant, looking out for what intensive properties are they giving me? And then as you start going through the problem, maybe they aren't all given to you, and you might try to figure out, well, which one of those can I figure out to fix the state? So they've given us two independent intensive properties. They've given us the quality and they've given us the temperature at state 1. So state 1, I won't have a problem fixing. But state 2, you see, the only thing they give me is the temperature. So I need some other property with which to fix that state. And whenever you have in this class, if you have, sometimes we'll have these rigid tanks. So what that means is you've got something in the tank and the walls are rigid such that even if you increase the pressure, the walls are not going to deflect, right? So you're not going to have expansion. And conversely, if your pressure decreases, it's not like those walls are going to cave in on one another. They're going to stay rigid. And what that means is that the volume is going to be constant. So that means that the volume at 1 is the same as the volume at 2. And that's because it's a rigid tank. And then the fact that, all indication is that it's a sealed system, right? You haven't opened a valve, you're not allowing water to escape. So it's a closed system, and so by definition, your mass is constant. So you got this closed system, so by definition, mass is constant. And so, well, your specific volume, which is volume divided by mass, a constant divided by another constant, that's going to be constant as well. So what that means is that your V1 is going to be equal to your V2. So if you see, it's a rigid tank, you're thinking my specific volume. My volume doesn't change, my mass doesn't change, so my specific volume doesn't change. So that's important. So if you have a rigid tank, that's the first thing you should be thinking. Okay. So we want to find the initial and the final pressure, each in bar, and we want to locate those on a PV and a TV diagram. So I've just put that we're going to draw a PV and a TV diagram because, in correctly drawing those, we're going to find those pressures. So on a PV diagram, you need P1, V1, you need P2, T2, P2 and V2. And then on a TV diagram, you're going to need T1 and V1, T2 and V2. So I need all of those things. And if I kind of look at what I've got for state 1, I've got the temperature, got the same thing for state 2, but I need the rest of those properties. So great. So now I got sort of a roadmap of where I'm going and the information that I need. So I'm going to go to my tables and I'm going to pull out those properties. But when I use the tables, I need to know what tables to go to. Am I going to the saturated tables, the superheated tables, the compressed tables? What am I going to? State 1, it's pretty easy because they tell us point blank, you've got a saturated vapor. So it's saturated. So it's saturated. And that's because you have a quality. And so all you're going to be going to is go to the saturated tables, go to the ones that are organized by temperature. And since your quality is 1, any properties that you want are going to have a subscript G after it. It's going to be right on that saturated vapor line. So it's going to be here. So you know that your specific volume is going to be the V sub G at T1, which is 0.1274 cube per kilogram. And then the other thing we need, of course, is our pressure. And because it's saturated, there's only one possible pressure that it could be at. And that's 15.54 bar. Perfect. So we went ahead and fixed state 1. We need to fix state 2. So like I said, since you've got this rigid tank, that's your other property that you know, right? You know T2, that's 100 degrees Celsius. And now, because you've made the assumption that the volume is not going to change, and you got this closed system, same as V1, 0.1274 meters cubed per kilogram. So now we got to figure out what phase we're in. So we're going to go to the saturated tables. I'm going to go to the ones that are organized by temperature. I'm going to go to the saturated tables to figure out what phase I'm in. I don't necessarily know I'm saturated. So at 100 degrees, I know that if my water is saturated, it's got to be between the V sub F and the V sub G value. So it's got to be between 0.001043.5 meters cubed per kilogram and 1.673 meters cubed per kilogram. And it is. So it's between our V sub F and our V sub G value at 100 degrees Celsius. So saturated.
And if it wasn't?
And if it wasn't, so if your specific volume was greater than that V sub G, then you would know that it was superheated. That's actually, it's Friday. I think we're going to end up needing to, and I say we, I'm going to end up needing to invent some new problems. So I think we'll solve this where state 2 is superheated and see what happens. Oh, that's a good idea. We'll solve it for what if it's not like that? What do you do?
Are you gonna give us information about the test on Friday?
Nothing more than I've given you so far. So I mean, like, all you need to do is bring in something to write with and a cheapo calculator, right? Something that's allowed on the FE exam. Basically, just something that's a non-graphing, non-programmable calculator. That's it, right? And then I will provide the tables, the equation sheet. So that whole PDF packet, I'll have those printed out and I'll let you borrow them for the test. So I'll pass them out and then you just give them back to me, and that's how we'll do the test from, for the rest of the semester, is I'll hand those tables out and then collect them back up. So the test itself will be similar to the practice test, in which you'll have 5 conceptual questions, which will probably be like multiple choice, where you should be able to knock those out in like 2 or 3 minutes. And then depending, I haven't written it yet, so it's going to be either 1 or 2 problems. Probably 1 problem though, just because we only have 50 minutes and I want to make sure that you have enough time to go through and really not rush. So either 1 to 2 problems, but probably 1. Okay. And then when
do we have to upload it onto Canvas in that submission thing?
Yes. So when you hand in your test, like, you'll come up like a normal test, and I'll have my desk up there, or I'll have a table up there, and you'll just you'll bring up your test and just bring your phone, and scan it and upload it to Canvas and just give me the hard copy, and then you're done. Okay. And that way my grader immediately has access to it and can hopefully start grading it pretty quickly and give you feedback a little bit quicker. Sound good? Okay. So for state 2, we've established that it is saturated. we've established that it's saturated, and so, yeah, there we go. So our P2, we've got that guy. So our P2 is our PSAT at 100 degrees Celsius, which is 1.014. Okay. So now we're ready to put things on our TV and our P diagram. So let's draw a diagram here. Sky and bar. Sky specific. Sky will be our TV diagram. All right, so both phases are saturated. So that's good to know. Kind of shaped a little bit differently, but I'm not, as long as you got a dome there, that's good with. So state 1, right there on that saturated vapor line. And then state 2 is going into the 2-phase region, right? It's going to be it's going to be underneath the dome. So my T1 is at 200 degrees Celsius, and then our T2 100 degrees Celsius. And then this guy, V1, V2, they're both 0.1274 meters cubed per kilogram. And then over here, same thing, starts out on that saturated vapor line and goes into that 2-phase region, and it's going to go straight down because it goes along a line of constant volume. So this is 0.1274 meters cubed per kilogram. E1 we figured was 15.54 bar. Then state 2 was 0.014 bar. And that's it. So what I'm looking for when I grade your TV and PV diagrams, I'm looking for let's make that a little darker. I'm looking for state 1 and 2 on relationship to the dome, right? Is it on the dome? Is it under the dome? Is it to the left? Is it to the right? So make sure that dot is in the right place. And if it's a PV diagram, you got PV labeled, or I guess for a PV diagram. So you need P1 and P2 labeled, or P1 and P2 and V1 and V2 labeled for that PV diagram. Same for TV on TV diagram. And then the other thing, and make sure you have your units, and then the other thing, the process path. So it's pretty easy, like for a constant volume process, because it's going to go straight up and down, right? Your volume doesn't change, your specific volume doesn't change. But say like, and I'm going to draw something here, and I'm going to erase it in just a second, but let's say that state 1, maybe instead of a constant volume process, maybe you add a constant temperature or constant pressure process. So maybe you started out on state 1, but it's a constant pressure process to some other state 2. Well, it's got to be along that line of constant pressure. right? So maybe it was a constant pressure to 300 degrees. So state 2 would be right here. So just make sure that your process path is correct. Is it a constant volume, constant temperature, constant pressure process? Right. Maybe none of those things are constant, but all right. So problem 18. Got water in a closed rigid tank. Starts out at 520 degrees Celsius and 100 bar. Then we got a final temperature of 270 degrees Celsius. So this is another example. We've got that rigid tank, so it's the same thought process. So our volume is constant. That's because we've got that rigid tank. And then we've got our mass, which is constant, just because it's a closed system. And so, specific volume, constant divided by another constant, is constant. So we know that V1, specific volume at state 1 and state 2 are the same. All right, so, and we wanted to find the final pressure, and I'm sorry, that's not P1, that's P2. We want to find the final pressure in bar, and then we want to sketch it on a TV and a PV diagram. Perfect. So I need to figure out, in order to solve that, I need P1, 1, P1, T2, 2, P2. All of those things. So of course I know T1 and T2. I've got P1, and then if I figure out what V1 is, I'll have already figured out V2, and I just need P2. So I'm close, almost there. So state 1, I don't actually know what my phase is, so I'm going to go to the information here. I got temperature and pressure, so it doesn't really matter. You can look up in either table. Now, if I looked up in my temperature table, T1, 520 degrees Celsius, P1 was 100 bar. And so where the problem comes in is I see that I am off the chart. The last temperature data point on that saturated table is 374.14, which seems an oddly specific number. And that temperature is the critical temperature. And it's that critical temperature, and it was mentioned in one of the videos, probably like 1.4, 1.5. But the critical temperature is the temperature at the top of that dome. And it's specific to the substance. So the critical temperature for water is 374.14, the critical 74.14 degrees Celsius, and the critical temperature for another substance is something else. And in fact, I looked in table A1, that now. So if you look in table A1, you see that you actually do have these there's critical temperature, that's the temperature at the top of that dome, and then the pressure at the top of that dome is called the critical pressure. So for water, for example, your critical temperature is this 647.3 Kelvin, which is 374 degrees Celsius. And then your critical pressure for 220.9 bar. So if you're above that critical temperature, it's more specifically classified as what's called a supercritical fluid. But if you're looking for the data, that data is all in the superheated tables. So more specifically, it's what's called a supercritical fluid. But for our purposes, the only thing we really care about is the fact that the data is in superheated tables. So that's where we're going. right. And we'd get to the same conclusion that we needed to go to those superheated tables if we looked at table A3. So you're at 100 bar, and you could see, okay, well, my temperature, 311.1, it's greater than saturation temperature at P1. So we're going to go to the superheated tables. All right, and so something that I realized in the previous class, the previous thermo class, is that while it says A4, what I think happened is I think I flipped a little section out of the compressed tables. So this is actually the thing. Just bear with me. It's okay. We'll actually flip to the relevant table. So we're at 100 bar and 520 degrees Celsius. So table A4, you're looking for the correct pressure. So you could see here 100 bar, 520 degrees Celsius. That right there is our specific volume. So you're just reading it straight off the table. And so, yeah. I'm actually going to, it's not that one. Actually gonna paste it here. Think. Aha! Done it. All right. So table A4, 100 bar, go to the temperature that you're interested in, and that's my specific volume. So my V1 is 0.0394, and it's meters cubed per kilogram. And then for state 2 over here, well, your T2 is given to you as what, 270 degrees Celsius. And then we've already said it's a rigid tank, so V2 and V1 are equal to one another, 0.03309 meters cubed per kilogram. So you need to figure out what phase you're in. So I'm going to go to those saturated tables, not because I'm automatically assuming that it's saturated, but because I want to use the information there to figure out what phase we're in. So table A2 organizes by temperature. So at 270 degrees Celsius, if it's saturated, then it's got to be between the V sub F being 0.0013023 cubed per kilogram, and this 0.03564 meters cubed per kilogram. And it is. So it's between that V sub F and the V sub G. So it's saturated. And that means that there's only one possible pressure it could be at, and that's the saturation pressure, Psat, at 270 degrees Celsius, which would be 54.99 degrees Celsius. Okay, so I've got enough information here to draw things on my PV and a TV diagram. So I'm going to do that now. Here's my PV. It's a TV. Bring it up. So, zoop. Go. So So state 1, remember we were actually above that critical temperature. So this is T1, that was 500 in Celsius, so 520, I think. Yeah. So here's our state 1. If you're interested, right? It's not necessary to put it on here, but that critical temperature was 374.14. And then it's a constant volume process. And you're going into that 2-phase region. I think I need to actually scoot this over. So if this goes down here, it's got to be in that 2-phase region. There we go. Sometimes you got to make it work for you, right? It's in that 2-phase region. Here's my T2 270. And then this guy was 0.03394 meters cubed per kilogram. And then over here, so we were at 100 bar. And it was in the superheated region. Remember that critical pressure. If you look it up in table A1, the critical pressure at the top of that dome is actually 220 bar, 220.9, I believe. So it's actually below that. So this is our P1, 100 bar. Then it's gonna go down into that. Go straight down into that 2-phase region. So it's our P2. P2 was 54.99. That 0.03394 cube per kilogram. Okay. So we've only, like I said, you know, I have to make up a couple of problems for the next time. So might like kind of repeat problem 17 or problem 18 to where instead of, you know, state 2 maybe being in the saturated region, maybe it's in the superheated region. And I think we're going to do a little bit more practice with interpolation, especially in those superheated tables, because sometimes it's not as obvious of how you kind of set up that interpolation piece. Okay? Very good. All right, we all stay warm. Enjoy the rest of your day, and then I will see you on Friday, okay?
I actually had a question real quick.
Sure, yeah.
So, you said you're giving us an equation sheet on on our test?
It is. So here's what this whole packet. That's what I'm giving you. All 96 of those pages in that order. So that's
okay.
Yeah. So make sure, clearly not written, but just make sure that you're used to, as you're going through problems, make sure you're kind of used to flipping through it. I mean, there's a table of contents, but you know, just be familiar with where stuff is. There's a lot of extraneous stuff, but kind of have an idea of where the stuff that you need is.
Yeah, understood. The main thing I was questioning is one thing I was trying to memorize is the like T, if T is less than T sat at P, it's compressed liquid and all that stuff. So I remember I thought you said something about we need to like memorize that kind of stuff.
Yes.
So I was curious. Okay, so that's not on there, correct?
That's not. So if you don't see it on the PDF packet that's on Canvas, then no, it won't be on there.
Okay, yeah, that's one thing I was wondering. I guess I needed to memorize that stuff a little bit better.
Yeah.
All right, just making sure. Thank you.
Okay. Yep. Alrighty. All right. So office hours tomorrow. I don't remember when they are, but sometime in the afternoon with the TA. But it's should be on the homepage. Okay. All right. Thank you guys. Y'all have a wonderful day.